So, as you can see, today we are going to talk about chart visuals. But before we dive in, let's take a quick look at a few financial charts. Some people want to see a simple, complex market pattern, like simple moving average. Others wants to see a complex visualization. And some gets really creative. And here, the interesting part, all these charts were made by ordinary users. Traders who want to uncover some insights, test their ideas. So here's the challenge. How do you let users write their own analytic logic without breaking performance? It's about finding a balance which gives users freedom while keep the system reliable for millions of traders. And today, we will walk through this journey together, from the idea to visualization. Let's start from the idea. Yeah. Let's imagine that we are traders. What we actually see at our starting point. Let's go to the platform itself and try to repeat user story. Every chart represents market data. Each point, candle, or line you see is based on information that the system received for a particular exchange for a specific symbol. So our first step is to select this symbol, financial instrument. For example, I'm interested in Apple stock. This financial instrument is trading on NASDAQ. Here we can see it. And this exchange is sending to the system a stream of raw data. This raw data is trades. Each trade represents a single deal between two market participants and has three key parameters: time, volume, and price. And using this raw data, we've already could display it, as you can see. But actually, it's hard to analyze. I can understand anything from here. Only less than % of users prefer such a detailed view. Most of them need more structured information. So our next step is to select aggregation method. It's a rule that tells the system how to group our trades. And the most common one approach is time-based aggregation. Trades we're grouping into the same time period. For example, 1 minute or 1 week. So let's choose 1 hour. Not once. Yeah. And display any view. Okay. We will see this picture. The system calculates in every single time period the key parameters: highest priced, lowest priced, close, and open prices. And here we can see these candles. Depending on their goals, each trader has decided how to aggregate this information to see the clearest picture of the market. So now we can actually see something. And our next step, our final step, is to actually analyze that. For example, I'm interested in how my lowest price changes over time. I can draw a simple trend line, connect this lowest price with that. And I will see that from this time period, my price changes like in this amount. Okay, I get it. But what if I want to go deeper? What if I want to see the plot of my lowest price, how it changes over time? And here the problem. I can't do it manually. It requires calculation and recalculation with every new trade. So, traders need a flexible tool to represent their idea, something that helps them express it like algorithm. So I think most of you have already guessed what we're going to talk about. They need a programming language. But not any language. They need one specialized for financial data. And here where we start our technical journey. Programming language built for one specific domain is called domain-specific language. Such languages provide high level of abstractions and use concept for a particular field, for example, financial data. And it's not unique approach for our platform. Most trading systems use the same way. Most of them create their own DSLs to make analytics easier. So, okay, we understand that we need a domain-specific language. And now you can ask me the reasonable question. Why just don't use existing language? Why not let the users write their idea on Python or Java? And here, big downsides. The first one is integration cost. Bringing the full programming language into trading chart is a massive engineering task. It requires adapting runtime, libraries, security, and tooling around that. The next point is that general proposed language doesn't support financial data out of the box. So we would need to create libraries for that. And the last point, accessibility. Not everyone who trades are developer. Giving them C++ or Python would mean forcing them to learn complex language from scratch. I don't think they need it. Traders need approachable and something simple. Okay, now we have our DSLs, which bring us to the next question. Where should we actually write this code? And we could, of course, ask our users to install separate application or use external editor. But actually, they are already analyzing code right here in the browser. So the most native place would be to code right to the chart itself. And this is mean building the IDE entirely on web. But what does it actually mean? To make users feel that they are working in a development environment, we need to adapt highlighting, auto-completion, error handlings. And I can continue this list longer, but already this feature helps them to write this code. And of course, we could write this feature from scratch by our own. But it would be faster to use proven foundation, like libraries. For example, Monaco Editor, or Ice Code, or Code Mirror. There are some libraries existing for this type of issue. In our product, we use Monaco Editor, actually. So, okay, we have this foundation. But there are no libraries that would support your custom language out of the box. You need to analyze this code, process this text, and we use for that issue language engine, where we would analyze it. But how our editor and our language engine should communicate? And here, the last thing we needed. LSP, Language Server Protocol. It's just a protocol like HTTP requests to communicate with editor. So our language engine analyzes this code and then transfers this information to our editor, where we can display this information. And with this setup, we could actually build the IDE that will run entirely on the web. But what about language engine? Where could it should be processed, where it should be? And we have three main approaches for this type of issue. We can execute compiled our code in local machine. In this setup, we use user's machine, so we don't need extra infrastructure. We will not have network delay. But here are some downsides. First of all, we depend on user's machine. We limited by CPU and memory. Also, performance differs widely between devices and browsers. Also, heavy code can block UI. Some limitation of pure local execution can be reduced by running code in sandbox, for example, WebAssembler. Here, we improve security and stability, but we still have this limitation. We still depend on user's machine. And the last approach is cloud execution. Here, we lost the most advantages of local execution, so we will need complex extra infrastructure. It would take more development time, and we will have network delay, of course. But running code in cloud means predictable performance, stable and predictable performance. We can reuse parallelized scripts between the users. So in our company, we decided to rely on this cloud execution. So let's think about it. Our user code in editor, browser-based IDE. This text is sent to a compiler where it analyzes, and all this information about errors, warnings, highlighting, all of this returned back to the editor, where we can display it using Monaco editor. Once the script is valid, we can execute it on our runner on live market data. And then this execution information can be transferred to our chart. And let's not go any deeper into server part and go with this data back to the chart. But how do we actually transfer this information? Let's remember what type of data we are dealing with. It's thousands of elements that could change every second. So our main goal is to reduce payload size and avoid network overload. We use a stream, so we need to use a WebSocket to transfer this information. One persistent connection, so we will avoid HTTP request. Also, to minimize traffic, we use some optimization. The first one is JSON plus compression. The next one is array-based format instead of object format. And the last one, we send only what has changes, incremental updates. And using this technology, we can reduce our payload size. So we arrived to the chart, our final destination. And here we have a big problem. We need to render all this information. We need to render a graphics. So let's see different approaches how to render graphics. The first one is SVG. It is browser-based format where we will have like DOM elements with every shape we will need to display. The next approach is Canvas. It is a CPU-based API that have a lot of built-in function to draw. And the last approach is WebGL. It is GPU-based API. It provides high performance, but it's really hard to develop. So we can understand it technically, but what does the number say? At around 3,000 points, Canvas starts quicker, yes. But once you start to interact, once you start to re-render this information, WebGL is faster. Always it starts faster. Independent tests show the similar pattern at a bigger scale. So SVG and Canvas drops performances at around 400 nodes. But if we talk about WebGL, it works fast, even under millions of elements. But WebGL doesn't support text out of the box. So if you want to display text, you need to use images, but it would reduce performances. But the main downsides here is complexity. It's not another API. It's another way to develop. It's low-level programming. If you don't believe me, let's try to code. Let's draw a simple circle using each pieces of technologies. Let's start with this SVG. Here, we have one DOM element SVG, which display the area where we will draw. To draw a circle, we need to add a circle. And as you can see, it's a DOM node. So if I want to draw something else, I would need to add more circles, more elements. Let's continue with Canvas. Let's see what we have here. Here we also have a DOM node to represent the area where we will draw. But here, to draw, we use JavaScript. We will need to get a context of our drawing, add attributes. And here we have a built-in function to draw circle, arc. So it's easier, but as you can see, we don't need extra DOM node, extra elements. All that we draw is a pixels inside our buffer. And the last approach, WebGL. Here we also have a circle, but to draw this, we need to make a lot of preparation. We need to, of course, get a context. At every point we want to draw, make it into buffer. Then we need to create a programs. We need to link these programs, use these programs, and then add the colors of each pieces of point. And only after all this preparation, we could actually draw our array of point, and we will get this circle. And also, this part, we need to draw our stroke. So, as you can see, we have a full control of drawing, but it's much bigger amount of development. So, all these approaches is valid. And it always depends on your project needs. If you develop games, for example, or something that change rapidly, it's better to use WebGL. If you have something slower, it's better to use Canvas. And if you have a static visualization like icons or small UI, you need to use SVG. And if we talk about trading, chart, it's something between. Yes, we have changes a lot. It's constantly changing something, but not as rapidly as games. So some system decided to use WebGL, some Canvas. In our product, we decided to use Canvas. We decided to focus on optimization rather than low-level programming. So, the whole path in one short take. Our users write a code in our editor, browser-based IDE. Then this text is sent to a compiler where we analyze it, and this structure information returned to the editor, where we can show errors, actually, for our users. Once the code is compiled, we can execute it. And this text, compiled text, is sent to a runner where we execute it on live market data. And this execution information returned back to the chart using one connection, one WebSocket. And here on the chart, we represent it using Canvas. After all tests, this architecture worked the best for show traders' ideas. And in the end, we don't just render numbers. We help users to see how their ideas work as a part of the interface. In the end, we have the system where users write code and instantly see the result. Scripts compiled in about 1 second. The chart maintains 60 FPS, and users can learn multiple indicators and strategies. So, and that's how we turn actually users' written script into lifetime visualization. Thank you, everyone. I hope you enjoyed the talk.